Okay, thank you for the introduction. So I won't show you any devices here, but I will talk about how we can make up new hybrid molecular scale materials, and by that I mean how can we take semiconductor materials, other light emitting materials, and embed them with plasmonic structures on the molecular scale, so on 1 to 10 nanometers or so, and create tailored optical properties that we can then think about these as new building blocks for devices in the future potentially. So we know a lot of properties are not intrinsic to the materials themselves, but are actually occurring in a fine interplay with the nanoscale environment around our materials. So by changing the local electromagnetic fields and therefore the local density of states, we can significantly modify properties such as the absorption and the spontaneous emission rate, as well as the ratio between various decay channels, and thus the quantum efficiency of our materials, as well as the radiation pattern. And we can do that in a number of different ways. As you probably know, we can use high Q cavities, such as photonic crystal cavities, or we can put our materials in very small mode volume structures, such as created using plasmonic bow tie nanoantennas, as shown here. So in that, by this creating and fine-tuning the environment around our emitters, and that we can control all these properties very significantly, means that then in turn it could have a potential impact on a lot of devices in the future. Even though I won't show you those devices, I do hope that it can push the frontiers there. So by enhancing the spontaneous emission rate, you could imagine much brighter and ultra-fast light-emitting diodes. Enhancing absorption rate significantly, you could imagine, could have a profound impact on photodetectors and light harvesting. Also, these intense fields could be good for catalysis, bioimaging, and well as sensors. And also the enhanced fields can be good for enhancing nonlinear interactions, and I will show you some examples of that tomorrow. And if you get to the single quantum emitter level, which I will also show you tomorrow, this could be interesting platforms for quantum information science as well. So in this way, I hope that we can start making new materials that are very different from what we can find in nature naturally, and that it could have an impact in a lot of different areas, both bio, as in this node, as well as energy applications, both from enhanced absorption, but also from the point of view of up conversion or down conversion, which could allow you to utilize a larger part of the solar spectrum. So I think there's a lot of exciting potential if we can try to see how much we can push these intrinsic properties of materials by modifying the environment around them. But of course, there's a lot of associated challenges with this as well. So for high Q cavities, such as these photonic crystal cavities, you actually see pretty modest enhancements in the spontaneous emission rate or Purcell factors, limited by a factor of 30 or so. It also requires intensive nanofabrication, as you can get the impression from this AFM image, and naturally have a narrow line width in that the high Q cavities, which is less desirable for certain applications. For example, if you are coupling it to broadband room temperature emitters, or if you're trying to make some network for quantum information science where you need to align each emitter with the cavity mode, and that can be tricky. Of course, plasmonics is not without its own challenges. So one of them, as we've seen, is that we get very large enhancements if we have small gaps, but the desired gaps are really less than 10 nanometers. So then we run into these same challenges with nanofabrication, both of the individual gaps as well as gaps over the scalability of creating arrays of small gaps. And we also, in that we introduce additional materials, these metals, we also introduce additional loss channels. So we have to mediate that as well. So in this talk, I will show you how we can actually overcome these first two challenges by utilizing self-assembly and colloidal techniques from chemistry, and how we can address these losses by using very well optimized structures that are maintaining a high radiative quantum efficiency, above 50%. So a lot of work has been done utilizing these plasmonic field enhancements for enhanced properties of emitters, such as creating fluorescence enhancements for Murner's group using bow tie nanoantennas and placing single molecules in the gap here, showing enhancements in the fluorescence about 1300. We can also create directional emission, which was shown by Nick van Holt's group, using this Yaki-Uda antenna, which can help you direct the emission into a desired direction. And finally, we can create enhanced spontaneous emission using this structure with a silver nanowire on top of a silver ground plane here with a small gap in between. And here, Evelyn Hu's group at Harvard showed enhancements about 1,000 times in the spontaneous emission rate. So a lot has been done in the field, but I think there's a lot of challenges still. Some of this is how can we achieve this large spontaneous emission rate while maintaining a high radiative quantum efficiency, which is really critical if we want to use this emission for something other than heating up our materials, which is desired for if you want to kill a tumor or something, but not desired for optoelectronic devices. And I'm also interested in what are the ultimate enhancement for the tailored properties. How much can we push these new nanomaterials to have properties that are different from the bulk counterparts? One structure that I looked at a lot and that works really well is these nanoscale pads antennas. So these are an optical analog of a grounded pads antenna. They're shown schematically here, so they're these colloidally synthesized silver nanocubes. They're about 75 nanometers across. And they're placed on top of this metal ground plane with a small gap in between, which is defined using a dielectric spacer layer where we can then embed emitters, and the typical gap is in the order of 5 to 10 nanometers. This structure creates very high field enhancements in this gap regions, as you can see here, about 100 times enhancements, and they're supporting very small mode volumes. And when we're fabricating these structures, they actually look very much like the cartoon here. They're indeed single crystal silver cubes here, which you can see that are pretty nice, I think, and they're actually easy to synthesize. They have a lot of nice properties. One of them is that there's a strong dependence of the plasma and resonance, both in the gap size and the cube size, because these structures form sort of Fabrication cavity and supports gap plasma modes here. So if you're changing the length of these cubes, you're changing the resonance. And the same if you're changing the thickness underneath, you're also changing the plasma and resonance as well as the local field enhancement. So this allows us to that way tune the local field enhancement and the plasma and resonance independently. It also has this pads antenna design, which gives us very directional emission, as you can see here. So the red shows our measurements. So these structures are actually emitting in a single lobe normal to the surface. And we can collect about 84% of the emission into the first lens. And these grayed out areas is indicating anything that's outside the collection cone of our objective. This can seem a little counterintuitive, but you have to think that these are very soft wavelengths. These are only about 75 nanometers, whereas we have a wavelength of maybe 800 nanometers. And the final really important advantage of this structure is that we're utilizing a vertical gap mode, which allows us to use well-established bottom-up fabrication techniques in chemistry that can allow us to control the gap size in a single nanometer, which we wouldn't be able to do if we had a lateral structure that we fabricate using electron beam lithography, such as the typical bow tie nanoantenna structure. And the techniques that we then do to fabricate this is just simple evaporation of silver gold. Sometimes we actually use template stripped gold as well, just to have a less roughness of our surface. Then we put down alternating layers of positive and negative polyelectrolyte polymers. We use P8s and PSS. These are self-limiting monolayers, so that goes down just a single monolayer, which is about 1 nanometer each. It's a dip coating process. We simply dip our entire sample in one solution of the polymer, rinse it off, and dip it in the other solution. And we can continue this process of alternating layers until we have exactly the thickness that we like. And this works on both large area surface as well as conformal surfaces. And then we can immerse our structure in a solution of Sci-Fi fluorescent dye molecules, so we can spin coat quantum dots or whatever active material we like to put down. Then we put down these colloidal quantum dots that are cubes that are 50 to 100 nanometers, and they're slightly charged, so the whole thing is electrostatically adhering, and we wash off anything that's not sticking. And the cubes, are synthesized. Just following standard procedures here in the literature that's more than 10 years old. So it's just start with these precursors, wait a few hours, and we have a solution of nanocubes that we can then use for creating our sample. I don't know why that little thing showed up here. Get rid of that. Oops. Then we're looking at measuring our structures. And since these are very sub-wavelengths, of course we can measure them using a standard bright field microscope. So we use dark field imaging. You can see an example of a dark field image here of a sample with many different sizes of cubes. And you have white light that comes in at a high angle, and it scatters mainly at the resonance frequency of each of these nano antennas, which is creating these different colors. So these are showing the different resonances of each of these nano antennas. We use a home-built setup that allows us to measure all this in one setup. So we can first measure the dark field scattering, then we can look at one of these particles that we like to know exactly the resonance. We can then put this into a spectrometer and we can see the resonance spectra. And we can also look at the fluorescence spectra if we have emitters coupled here as well. And then we have another detector here, which is a single photon detector that allows us to measure time resolved fluorescence in these same particles. And we also have actually a an additional single photon detector that allows us to measure anti-bouncing and things like that I will show you tomorrow. So it's a pretty flexible setup. The first thing that we set out to look at here was just the simple fluorescence enhancement. When we put dyes, embed dye molecules into the structure, how is the emitted fluorescence modified, and how does that depend on the plasmonic resonance of our nanoantenna structure? So this is showing a smaller nanocube here. It has a resonance about 540 nanometers. And then we measure the same ones over here. So each of these green crosses is a single nanoantenna. And we can see here we are off resonance with both the emission and the absorption excitation. And we see basically no enhancement in the emitted fluorescence. If we then, on the other hand, look at a slightly larger nanocube here, this has a resonance around 630 nanometers, which is close to the excitation wavelengths of our laser, and which is also close to the absorption. In this case, we actually see fluorescence enhancements that's exceeding 30,000 times. This is when we compare it to a glass substrate and also normalize it per unit area. And then, of course, the natural question is, what does this fluorescence enhancement come from? You can see that we have most of the enhancement when we are close to the excitation wavelengths, and which is also naturally overlapped with the absorption. And that's also because this is mainly due to an excitation enhancement. So we're just more efficiently exciting the incoming light. There's also a contribution from an enhanced quantum efficiency from around 20% to 45 or 50%. And then the final contribution is from this modified radiation pattern. So if you just have dye, molecules, and glass, a lot of the radiation is actually sucked into the substrate. But since we are having these nanoantennas, we are actually redirecting this emission, which just means that in this case, we are collecting a larger fraction of the total emitted light. So we have these three contributions, and in this case, the main contribution for the fluorescence enhancement is due to a more efficient absorption of our structures. To get a little more insight into what's going on, here we can also measure the fluorescence lifetimes. The fluorescence lifetime of our dyes with the same spacer layer on glass here is about 2.5 nanoseconds. When we put these same dyes into our nanopads antennas, they have a lifetime that the shortest component is less than 33 picoseconds, which is limited by the instrument response. And in this case, this is measured from an example of nanopads antennas. I will later show you measurements also of individual antennas. And in this case, the way this is measured is using a femtosecond laser. So we come in with one pulse that excites the structure, and then we have a single photon detector, and that's time correlated, that can time tag the arrival of these photons when the light is emitted. But it's really important to take these shortening of the lifetime data together with the overall fluorescence enhancement, because we could also do another control here. You could say if you just put dye molecules on glass, on silver, and also have the same spacer layer in between, we will also see a shortening of the lifetime. In this case, we see 164 picoseconds. But in this case, we see that the fluorescence intensity is reduced around 20 times because of crunching due to this metal surface. But in this case, when we add the resonant cubes and do nothing else to the structure, we can actually get fluorescence enhancement up to the 30,000 times. So we're really in two different regimes, and in the case with the resonant nano antennas, we can really enhance the ratio to spontaneous emission rate. But it's a little unsatisfying to be limited by the detector response here, so we set out to understand what is the real enhancement in the spontaneous emission rate. And in order to answer that question, what we chose to do was to use dyes that has a long lifetimes. And in this case, we picked ruthenium metal complex dyes that has a lifetime on glass about 600 nanoseconds. So this allows us to use the exact same measurement technique with this time correlated single photon counting system. But now we should be able to, this has such a long lifetime, to be able to map out this large modification without being detector limited. And these ruthenium metal complex dyes also has a nice separation between the absorption and the emission spectrum here, a large Stokes shift, and also relatively good photostability. What we set out to do in this case was to understand how large enhancement can we get in the spontaneous emission rate, and how does this depend on the gap size. So in this case, we overlap the resonance of our plasmonic structures with the emission, because we predict that the largest enhancement in the spontaneous emission occurs when we are enhancing the emission as opposed to enhancing the absorption, as we did with the Sci5 dye molecules a couple of slides back. So in this case, we modify the gap size, and then we adjust the size of the cube so that we always have a fixed resonance at 630 nanometers to be overlapped with the emission. And this is what we see. So we see huge enhancements in the spontaneous emission rate when we modify the gap from 15 nanometers down to 5 nanometers. And this is all a big change from the control sample on glass, which is shown in blue here, which shows, just looks flat on this time scale of 40 nanoseconds. But to really understand what's going on here, we actually have to answer quite a few questions. One is, what is the distribution of decay rates? So we see that this is not a single or bi-exponential decay. It's actually a distribution and a lot of different decay rates. We also really have to understand the role of crunching versus radiative enhancement. As I said, for optoelectronic devices, we really want enhancements of the radiative components. It also turned out to be really important to properly understand the nanophotonic environment. What is the dipole orientation of these emitters, and exactly where in the gap are these emitters located? So I mentioned in the very beginning of the talk that we get a large enhancement over sort of a large area under a single cube, but it's not exactly homogeneous. So this is showing COMSOL simulations of the enhancement that's expected in the spontaneous emission rate compared to glass. So we see the largest enhancements near the corners of the cubes, and it sort of tapers up towards the center. So in this case, since we're not looking at single molecules, but looking at an example of emitters that are distributed randomly everywhere, here we're basically sampling all these different positions, and therefore we get a distribution of decay rates. It also turned out to be really important to be able to do proper simulations of our structures to understand what's the dipole orientation of these emitters. So we actually ended up building a completely separate setup, varying the incident angle and the collection angle, and doing a series of measurements and then a global fit to all these measurements. And from all that, we could extract what is the average distribution of the orientation of these dipole molecules. And what we found is that most of them are lying relatively flat at a 75-degree angle to normal here. The ideal coupling direction to our cavity is actually vertical, so this was not quite desired, but it showed that we could still get a very large enhancement, and we know how to optimize it. But this is really worse than random orientation of our molecules, which is often a natural assumption. But these are slightly charged molecules, the surface is slightly charged, so it's not surprising that we get this distribution. The final component that we also had to understand to get proper agreement with simulations was exactly where these emitters placed. So we put down these polymer layers that we put down our dye molecules, and then we sort of initially just thought, oh, all the dye molecules are lying in this little layer, but of course they're starting to intercalate into the surrounding polymer. And when we did a fit to our experiments, we found that if we assume a 2 nanometer vertical distribution of emitters into these polymers, then we get a good agreement with the experimental data. And why this is so critical is because the quantum efficiency, every time we excite an electron, how often does it emit into free space as opposed to non-radiative decay channels, depends strongly upon the Z position, the distance between the emitter and the metal interface. So we can see here, if you're assuming this 2 nanometer distribution, we can then average over these different quantum efficiency in our simulations. So I'm showing this just to show you sort of the types of scales and the type of accuracy that we really need to be able to properly understand and probe and tailor these properties. So when we take all these things into account, this describes the observed behavior very well. The final thing was this radiative versus non-radiative decay component. So unfortunately, we cannot measure the quantum yield or the quantum efficiency of our structure directly. What we can do is to ensure that we understand the time dynamics, the fluorescence decay lifetimes as a function of gap size, and we can also measure the overall fluorescence enhancement factor and compare that to simulations. So what we're doing here is looking at the overall fluorescence enhancement factor, which has these 3 contributions that I mentioned before. One is the modification in the collection efficiency due to this modification in the radiation pattern of our emitters. This we can measure, and I showed you those measurements earlier. Then we have excitation enhancement, so how are we more efficiently absorbing this incoming light. And we can also find this from simulation as a function of gap size. The same we can do for the quantum efficiency. So we can see this has opposite directions, so we have a sweet spot somewhere there. And then we can take these 3 things into together and obtain the fluorescence enhancement factor and compare simulations with experiments here as a function of the gap thickness. And we can see we have a good agreement here, which leads us to believe that we indeed have a high quantum efficiency. This is around 50%, but has a strong dependence on the gap size, and usually we work around a 10 nanometer gap. This is where we have this 50% quantum efficiency. So then we can go back to the data again and understand this in a little more detail. So let's just take the example of the 8 nanometer gap. In this case, from experiments, we can do a stretched exponential fit and then a Laplace transform to extract the rate distribution and the probability for these different rates to occur. And then the black here shows the simulations, and from that we can also extract these rate distributions, which is shown in black. The way to understand this is that this tail over here shows the maximum decay rate, which occurs shortly after the molecules has been excited, and shows a decay of 0.7 nanoseconds, corresponding to an enhancement of 860 times in the spontaneous emission rate. We can also look at the most likely decay rate, which is the peak here, about 10 nanosecond decay, corresponding to an enhancement about 60 times. So that was for the 8 nanometer gap. We actually also have a gap of 5 nanometer. In this case, the maximum total rate enhancement is about 0.3 nanoseconds, corresponding to an enhancement about 2,000 times in the spontaneous emission rate. So then we can put all this data together as a function of gap thickness. So we can look at the maximum total rate enhancement, so that's all the tails, fastest tails. Here we can see this keep going up as we have smaller gap sizes, reaching a maximum of about 2,000 and a gap of 5 nanometers. The most likely rate enhancement follows the same trend, but just at a lower value, which is mainly due to these molecules' dipole orientations not being ideal. Then we can look at the maximum rate enhancement, or radiative rate enhancement, which is probably the most important thing, which is the maximum enhancement in the spontaneous emission rate times any modification in the quantum efficiency. So we can see at the larger gap sizes, the quantum efficiency is actually increased. So we get an even larger enhancement there. But as we go to the smaller gap sizes, this starts to taper off. And if you continue further here, this will start plummeting very quickly. So we get a maximum radiative rate enhancement about 1,000 times. And this is due to this increased local density of states and also the high radiative quantum efficiency of these structures. So it shows that we can really get tailored radiative properties by control of the gap size. And I think what's interesting here is to look at the scale. So if we just change it a couple of nanometers over here, we can actually change these properties significantly. So really having ways of controlling the gap on this single nanometer scale, which is well beyond electron beam lithography, at least electron beam lithography available at most universities, then this really gives us insight and ability to create new nanomaterials with properties that are far removed from the bulk counterparts. So to summarize here, so I showed you fluorescence enhancement exceeding 30,000. I showed you this large increase in the spontaneous emission rates. And I talked about how I think these new hybrid materials with very tailored properties is super exciting, and that we need to create a controlled critical feature sizes. So I'm not saying everything needs to be controlled with 2 nanometers, so it's the gap that needs that kind of control. The control we have of the size distribution of cubes is about plus minus 5 nanometers. This is also sufficient here. So controlling these sizes of some critical features is really key. And a little bit of outlook, so I think this is exciting for potentially enhanced bioimaging, that you could maybe make more brighter fluorescence labels or more efficient sensors, that you can use these new nanomaterials by design for ultra-fast optoelectronic devices that could operate at lower powers without thresholds as you need for lasers. And I also think it's really exciting that when we started to make nanomaterials that are deriving the properties from the surroundings, to think about modifying those surroundings in real time, which in turn can allow us to get reconfigurable properties. So I also just want to acknowledge my group at Duke, my collaborator, and this work, David Smith, that did the simulations of the work, as well as funding agencies. So thank you so much for your attention, and I would be happy to take your questions.